Alright, so welcome to this tutorial on half-life for the AP Physics, IB Physics Year 2 course. So we're going to be talking about half-life, talking about the mathematics of it, but before we do that, we're just going to review a little bit about nuclear stability. So we did an activity in class where we were looking at creating a graph of binding energy per nucleon versus the number of nucleons, the mass number. And what we saw was that there was this curve that there was a drastic spike up, and then there was this kind of tailing off. Okay, and we kind of talked a bit about that the greater the binding energy per nucleon, the harder it is to put it together, but it also consequently means that the harder it is to break it apart. So it leads to this idea of stability. And so what we kind of concluded from that is that the greater the binding energy per nucleon, the greater the stability of the nucleus. And so we also talked a bit about fission versus fusion, and this idea of yield, meaning you get energy out, excess energy out. All right, so if it's on this side of the curve, okay, so nuclei to the left of the peak will produce excess energy from a fusion reaction. Okay, and then if it's on the right side of the curve, then we'll produce excess energy from a fission reaction. Okay, and that just has to do with the fact that here we have where we have basically lighter elements, so coming together produces a greater stability, and here we have heavier elements, so breaking it apart. The magic number for a fusion is right around the atomic number of 82. All right, so let's take a look at an example. So we have iron 56, and we know the mass of the iron is this, and then it's made up of protons and neutrons, 26 protons, 30 neutrons. And we know that the masses of the constituents have to be greater than the mass of the iron in order for this to kind of stay stable. So if we do a mass defect, we start off with the mass of the iron 56, and so as we said, we have 26 protons, so 26 of these guys. It's 1.0078. This is universal mass units. And then we have 30 neutrons. Okay, so we have 26 protons, 30 neutrons, and you can check my math on this, but I got a mass defect of about a half of a universal mass unit. And then if I figure out how many MeV that is, if I do the 931 MeV in one universal mass unit, I get 492.4. And then if I want to find the binding energy per nucleon, I take that binding energy and divide it by the number of nucleons, so in this case 56. And so I end up getting the 8.79 MeV per nucleon, okay, which is right at the peak of this graph. Okay, this is our most stable isotope that we know of. So basically, if we want to understand this, the graph, okay, does not directly indicate, okay, so does not directly indicate whether a nucleus will be radioactive or not. Okay, so in order to kind of figure out that, remember, radioactivity does not mean lead to stability or not. It's just that things that are more radioactive will more spontaneously decay through the alpha, beta, or gamma emission. All right, so in order to kind of get the idea about radioactivity, what we need to take a look at is the number of nucleons left versus the Z number, the number of protons. All right, so kind of review a little bit here. As mentioned in other lessons, certain nuclei are unstable and will spontaneously decay either through an alpha, so a helium nucleus, beta, an electron or positron emission, or gamma, a photon. And furthermore, that any ore of a particular isotope is comprised of a vast number of nuclei, and which do not decay all at once, but rather this happens one by one over a period of time. Okay, so within each sample ore, it will decay completely and utterly random. Okay, the important point to take away at this moment is that this process is completely random. We cannot look at a given nucleus and say that nucleus is going to decay in 3 days. However, what we can do is we can say approximately how many nuclei will decay in a given period of time using the mathematics of probability. Okay, this is a probabilistic event. So we can say how many of a given sample are going to be left over a period of time. Okay, and that's going to introduce the idea of half-life. All right, so before we get to that, we want to talk about the rate of decay. Okay, also the what's referred to as the activity. Okay, so it is the negative rate of decay. Okay, the negative piece just means that we're losing nuclei that are radioactively decaying. And so it is defined as the negative of the change in the number of nucleons over the change in time, the period of time, the time interval. Okay, and its units are a count per second. We'll talk more about the details of that, but we define it as the metric unit, the becquerel, which is actually got a unit that's counts over seconds, so really it's a unit of seconds to the -1. Okay. Then we also have something referred to as the decay constant. Okay, and it's given the Greek symbol lambda. Okay, this is not wavelength. This is another quantity that's using the same letter. And it's a property of the nucleus that determines the probability. Okay, well, there's that word again. The probability of a particular decay. The interesting about both of these is that both the activity and the decay constant are not affected by any environmental issues. Okay, whether we're talking about temperature, of the surroundings, it's even independent on the amount of the sample that you have. All right, so the equation for the activity, as I said, it's defined as the negative change in the number of nucleons over time, the rate of change in the number of nucleons, which is equal to that decay constant times the number of nucleons left. All right, so what we see is that the n is the number of the original nuclei still present. Okay, so n decreases over time in a non-linear fashion, and in order to actually see this, we'd have to do some. We solve for n, and we have to do some integral calculus. But nevertheless, we would see that it decreases exponentially. And if you solve that for n using some calculus, you'd see the number of nucleons left is equal to the number of nucleons originally, the n naught, okay, multiplied by e to the minus decay constant t. Okay, and you saw this through the dissectivity. In the dissectivity, we created a graph, and we saw that it decreased in an exponential fashion. All right, since the activity is directly related to n, okay, then the original the number that is left, and that this decay constant is, as it's mentioned or as it's named, constant, the activity decreases exponentially with time, and that activity equation, basically very similar to this, but instead of n naught, it's a naught e to the minus lambda t. Okay, which if you relate the two equations, what you can see is that this is equal to lambda n naught e to the minus lambda t. Okay. So what is interesting about this is that you will not be responsible for this particular equations, or these particular equations, but they kind of give you some insight over the nature of radioactivity. So so let's talk a moment about this decay constant. As you might suggest, or might kind of gain some insight, is that the higher the value of this, the more radioactive. And so what we mean by radioactive is that it's essentially emitting more particles per second. And so there's going to be, over a given amount of time, there's going to be less of that sample left, so the faster it decays, and kind of conclude generally from this, the more dangerous the material. Okay, this is not always particularly true, but if it's ejecting more alpha, beta, and gamma particles, then you're exposed to them, then the more that you are exposed in a given amount of time, the more dangerous it is. All right, so let's take a look at an example how this might look in a problem. All right, so it says a mole of carbon-14 is present in an atmospheric sample of CO2. If the decay constant lambda is 3.83 times 10 to the minus 12 invert in a second, so becquerels, how much time elapses before half the sample is still radioactive? So our number of nucleons left is 1/2 of what it originally started with. All right, so we're going to start with the first equation that's up above, that the number left is equal to n naught e to the minus lambda t. And so what we're going to do first off is that we're going to try to get rid of this exponential. So if we take the natural log of both sides, okay, so we have the natural log of n equaling to n naught to the minus lambda t, okay, and then if I divide by n naught, divide by n naught, okay, and there should be a natural log here, then what I get is the natural log of n over n naught. Okay, and so we're going to make this substitution here, that the number of nucleons that are left is 1/2 of n naught. And so we get is 1/2 of n naught over n naught. You can see that those cancel out. The natural log is in front of here. Is equal to minus lambda t. All right, so if I bring that up here, then I have the natural log of 1/2 is equal to minus lambda t, and then so solving this for t, then I get I'm going to do 1 over the invert of lambda is equal to the natural log of 1/2. So if you go through and plug in for your lambda, check my math on this, but I got a value of 1.8 times 10 to the 11th seconds. And if you convert this into years, this is approximately 5,700 years. Okay, so this is obviously a long period of time, and you may have heard of carbon dating, and we'll talk more about this in just a moment, but this is how we do general carbon dating for organic materials. What is the activity of the sample at this time? Well, since we can kind of take a look that the activity is equal to lambda times n, okay, so the activity is equal to lambda times n. All right, and so once again, n is 1/2 of the original, okay, which we said the original is a mole. So 1/2 of a mole, Avogadro's number, 6.023 times 10 to the 23. This is approximately 3 times 10 to the 23 particles. And if I plug in that with the decay constant, the activity at that point becomes the decay constant, so 3.83 times 10 to the minus 12, okay, multiplied by the number left, 3 times 10 to the 23, and so I got an activity of 1.15 times 10 to the 12 inverses of second, becquerels. All right, so has the value of lambda changed in this time? And the answer to that kind of goes back up to this statement right here, is that lambda is always constant. Okay, it is dependent on the property of the nucleus, okay, and not anything surrounding it. So it does not change with time. So the answer to the question, has it changed, and the answer is no. Okay, lambda is constant. All right, so that concludes the video on half-life. We'll get into some of the nitty-gritty of the mathematics of the half-lives in class. Thanks for listening. Have a great night. Bye-bye.